In this video, I want to talk mainly about domain. I want to start with the domain graphically. So I've drawn a figure. We have a curve that's going from negative infinity, pointing downwards essentially, comes up and passes through the point -2, 0, -1, 1, where it closes with a dot. And then it restarts at 0, 0 with an open dot, and then we have the arrow that points downward and rightward from there. If we look at the domain, remember, we can think of as the x values, the first set of coordinates. Our x values, we're purely letting our eyes look from left to right. That's all we're considering. We don't care if it goes up or down at all. So as our eyes look to the left, we see that this arrow goes forever to the left. That's called negative infinity. As it comes back to the right, however, it stops at -1. So we have to stop our domain at -1. That's going to be inclusive. It has a bracket because of our dot on the end of that line. Now it resumes, so I have to continue. I'm going to do that with this little union sign over here. It resumes at 0. However, 0 is not included because it's an open dot, so I'm going to use parentheses. And it goes off to infinity from there. And infinities always get parentheses. Since we have the figure, it's actually pretty easy to get the range as well, because it's graphical. To do it algebraically using the equations, we're going to do that a little bit later on in the chapter, so not in this video. But here, range, we're looking purely down to up. And for domain range, whenever we're listing it using these intervals, we always want to have the smaller value first. So that's why I'm saying look down first. So we can see we go down forever and ever, negative infinity. As we let our eyes trace back up, it depends if we're looking at this leftmost figure or the rightmost figure. If we consider the leftmost figure I got that backwards, the rightmost figure rather, over here on the right, as we come up, we stop at 0, and 0 would not be included. However, I'm going to look at the picture in total, because over here on the left, that does continue to go through 0 all the way up to 1, where it ends with a firm dot. So really, the left side is more important than the right. Not that it's more important, but more telling. It's more comprehensive than the right-hand side. We go all the way from negative infinity to 1, and that is where we stop, and it is included, so it has a bracket, not a parenthesis. I'm going to jump over here to the second figure I've drawn. I'm going to do this one a little bit quicker. So if we consider the domain on this one, once again, we're going all the way forever and ever to the left, so negative infinity. As we come back to the right, however, we hit 0, we touch it, but we immediately pick back up with the bottom figure. So tried to illustrate that with a little blue line there. This does go all the way from negative infinity to infinity. There's not actually any meaningful break. Sure, there is a gap there in the center, gap here, but it's just not meaningful in terms of the domain. The domain goes from negative infinity to infinity. So anytime we can join those domains together into a single interval, we want to do that. For our range, we would have negative infinity to 1 once again, 1 in the bracket. Just to show a slight variation on this, let's change this end mark. Instead of to being a closed dot, change it to being an open dot. In that case, I would absolutely have to change that domain. My domain would go from negative infinity to 0. This time I can't join those zeros together because there is space in there. And so I have that 0 that's been removed in the second line of my domain. What would change in my range? I'd use a parentheses instead of a bracket. Right, let's get to the equations. We look at just some basic equations. Say 3x plus 2. Let's take f of x to be equal to x plus 4. Both of these, for thinking about the domain, again, that's all we're doing in this section, domain, the values that x can take. Really, an easier way to sometimes think about it is there something I cannot plug in for x? Is there something that causes my equation to have a problem? And in this case, there's just not. On both of these equations, on both of these functions, there's nothing that would cause me to take pause and say, hey, look, 3x plus 2, there's something I can plug in for x that causes a bigger problem in my equation. Same thing on the x squared plus 4. Everything I can plug in there is going to be fine, so my domain, negative infinity to infinity, all real values. At this point in the class, there's only 2 places we're going to have to worry about restricting our domain. One of those is when we have rational functions. So here is the most basic rational function possible, 1 over x. If I think about what I can't plug in for x there, I know I can never have 0 in the denominator of a fraction. So x cannot be equal to 0. That means if I'm going to write my domain interval notation, I'm going from negative infinity to 0, and then from 0 to infinity. I have to exclude that value of 0. We take another function, I'll call this one g of x just so we can have a different name. Have 3x plus 2 over 2x minus 1. A little bit more complex of a rational function, but the idea is still the same. I can't have 0 in the denominator. So what I'm going to do, I'm going to take that denominator, I'm going to set it equal to 0, really saying it's not equal to the 0. But I'm setting it equal to 0, slashing through that equal sign. I'm going to solve this just like I would any other equation. So 2x cannot be equal to 1, and x cannot be equal to 1/2. So my domain for the second g of x here, negative infinity to 1/2, and 1/2 to infinity. The numerator, 3x plus 2, I never touched that. All I did is I took the denominator, the 2x minus 1, set that equal to 0. The numerator doesn't matter at all in terms of the domain. The numerator can be whatever the numerator wants to be. If I have 0 up there, that's fine. 0 divided by anything is 0. It's just when the denominator is equal to 0 that I have a problem. Now, just because we see an x in the denominator doesn't mean there is going to be a restriction on the domain. So let's take 3x over x squared plus 1. If I try and take that denominator, x squared plus 1, set that equal to 0, I'm going to have x squared equals negative 1. I take the square root of both sides, put your plus and minus in front of it. Now, we haven't studied this yet, but square root of negative 1 is going to be an imaginary number. But at this point, we might just say, you know what, we don't know how to do that. Square root of negative 1, square root of any negative number we've always been taught can't be done. And so this imaginary number isn't going to play a part of my domain. My domain is just going to be from negative infinity to infinity. And that makes sense. If we look back at the x squared plus 1, remember what we're saying, we can't have 0 in the denominator. Well, if we take a number, we square it, it has to be 0 or positive. If I add 1 to that, I'm guaranteeing it's going to be positive. So there's nothing that I couldn't have there. So rational functions don't necessarily have a restriction, but they might that we need to try and solve for. So to set your denominator equal to 0, really saying that's what you can't have, set the denominator not equal to 0. The second type of equation at this point, we're studying at this point, that we cannot, that we're going to have a restriction on the domain, are square root functions, and in particular, really even root functions. Square root of x, as we were just talking about, we can't take the square root of a negative number, at least none stay real. Probably at this point, haven't really looked at those at all. Square root of any negative number, you've just been told you can't do it. Partially true. Can't do it and be a real number. So what we need to do is we need to take the inside of the square root. In this case, I have the square root of x. Let's take the inside of that square root, set it greater than or equal to 0. So in this case, x is greater than or equal to 0. So in my domain, I'd have 0, comma, infinity. The 0 gets a bracket because we can have the 0 under the square root. Infinity always in a parenthesis. Take a slightly harder one. G of x is equal to square root of 3x plus 4. Same exact idea. I'm going to take the inside of that root, the 3x plus 4. I'm going to set it greater than or equal to 0. And I'll solve it. So I'll subtract my 4 over, and I'll divide by my 3 and get negative 4/3. X to be greater than or equal to negative 4/3. So here, bracket, negative 4/3, infinity. So notice what I'm saying. I'm not saying that x can't be equal to a negative. That's fine. X can be a negative 1. Negative 3 plus 4 is still positive 1. What I'm saying is the inside of that root can't be equal to 0. So we have two different functions, rational functions, root functions, that we have restricted domains on. Rational functions, x is in the denominator. We want to set whatever the denominator is equal to 0, solve that. If we have a root function, we want to set the inside of that root greater than or equal to 0 and solve that. So what if I put the two together? Let's say I have 2x plus 1 over the square root of x minus 3. Now if we purely had the root function, the square root of x minus 3, we'd say, well, x minus 3 has to be greater than or equal to 0 because we can't have a negative inside that root. But because now it's in the denominator, what I have to do is I have to come back and I have to eliminate that negative, that equal to underneath the greater than sign. Because x minus 3 is in the denominator, I can't have it equal to 0. X minus 3 strictly has to be greater than 0. And so x will be strictly greater than 3. Our domain will be from 3 to infinity, but the 3 is now a parentheses, not a bracket. Otherwise, just about any other function you can think of. If we had an x cubed function, a cubic function, if we had a cubic root, h of x is equal to cubed root of x plus 2. Cubed roots, I can take the cubed root of a negative number, that's fine. So all those, they don't have restricted domains. If I had g of x is equal to the absolute value of x minus 2, that's fine. On all of these, the domain would be from negative infinity to infinity. Up to this point, like I said, the only two restricted domains, we're going to have rational and root functions. The one thing we're going to add down the road, logarithmic functions in this class. When we get to those will also have a restricted domain. And then as you move into other classes, you might find other functions that have restricted domains as well.